Number 16 is a straight power equals current times voltage problem. So we know the light bulb has a power rating of 60 watts, 120 volt outlet, so 60 divided by 120 volts gives us a current of 0.5 amps. Number 17 is a Coulomb's law problem. We have a positive charge at different locations, A, B, and C. Now, because there's 4 other charges that act on that positive charge, we essentially have 4 forces acting on the positive charge. So if we look at the kind of the free body diagram at each of the 4 locations, we know opposites attract and likes repel. The only possible option that there's no net force is when all the forces cancel out. So B is the only possible option. For number 18, monochromatic just simply means the different shades of a specific color. So, for example, different shades of blue. When light goes from one media to another, the frequency doesn't change. In fact, the frequency determines the color of the light. So the color of the light does not change. So what does change is the speed and then therefore the wavelength, because V is equal to F lambda. But the key here is that F will not change, because that would mean that the color of the light changes. Number 19 looks like a force problem, and it sort of is, but because the forces on this long rod are acting at different points, we have to think of this as a torque problem. So we know torque is radius times force. Now the key thing to remember about torque is that the radius and force have to be perpendicular to each other. So the force of gravity about the center of the mass of the rod, right in the middle, tau 1 we call it, we have to use the perpendicular component of that, which if we look at our diagram is actually the cosine of theta. So we set torque 1 equal to torque 2 from the string, and when those two equal each other, we get 1/2 mg equals the tension in the rope when we plug it into the equation. For number 20, we are dealing with a compound circuit. Now, the EMF of a battery, that stands for electromotive force. That's a fancy way of asking what is the voltage of the battery. So we know V is equal to current times resistance. We already know the current is 3 amps, but we need to know the total resistance of the circuit. So first thing we do here is we look at B, C, and D. Since all 3 of those are in parallel, we use our parallel resistance equation to get a total resistance of 1 ohm. And then we can essentially say that that 1 ohm is now in series with A, E, and F. So 3 plus 1 plus 3 plus 3 is 10 ohms. So 3 amps times 10 ohms gives us a total voltage of 30 volts. Number 21 deals with power, and the power dissipated in the resistors, or we're comparing different resistors. So generally we know power is equal to current times voltage, but we also know voltage is current times resistance. So if we're looking for a specific resistor, it actually makes more sense to use the equation P equals I squared R. How do we get that? We just took Ohm's law, V equals IR, and substituted that V into the P equals IV equation, leaving us with I squared R. So now we look at resistor B and resistor E, and we see that resistor B, that 3 amps of current actually gets split between B, C, and D. So resistor B only has 1 amp of current running through it. So when we plug it into the equation I squared R, we see that the power dissipated is only 3 watts, whereas in resistor E, it's still got 3 amps of current, resistance of 3 ohms, so 3 squared times 3 is 27, which is 9 times bigger than that of resistor B. For number 22, we are dealing with a Doppler shift, or the Doppler effect. Now the key thing to remember about the Doppler shift is it deals with relative speed. So if 2 objects are moving in the same direction at the same speed, with regards to each other, in relation to each other, they are essentially not moving. So you will not feel that Doppler effect if they're both moving at the same speed, which gives us the answer of C. Number 23, you kind of have to do some algebraic manipulation here. We're looking for ultimately the dimensions of power. We know power is work over time. Furthermore, we know that work is equal to force times distance, so we substitute that in for work. Then we know force, we can simplify that into mass times acceleration times distance over time. And then when we look at the units, we see mass is kilograms, acceleration is meters per second squared, distance is meters, and then all that over seconds. So when you do the algebra there, you see that the total units are kilogram meter squared over seconds cubed, which means that's essentially a mass times a length squared, a distance squared, over a time cubed, leaving us with answer D. Number 24 is a conservation of energy problem. Now, when do we decide whether we use for potential energy MGH or GMM over R? And the answer to that is really you kind of have to decide, is your height that you're dealing with, is it even comparable to the radius of Earth? Because the height is equal to the moon's radius, that means that's a pretty large height. So we're going to have to use GMM over R. So when we plug in our appropriate values here, the total distance, or R, is actually 2R because it's from the center of moon. So the moon's radius is already R, plus an additional height, H, which is equal to moon's radius. So the total height from the center of the moon that this object is being dropped is actually a distance of 2R away from the moon. So we go ahead and work our equations out, and we see that the velocity is equal to the square root of GM over R, giving us an answer of A. We're going to skip number 25 and 26. 25 deals with decibels, which really is not covered in this class, and 26 deals with electric fields, which also is not covered in this class. Number 27 is a pretty complex algebraic manipulation problem. So anytime we launch something at an angle, we know certain things, and we know this is a kinematics problem, a projectile motion problem. First of all, since we're looking for maximum vertical displacement, we know that the final velocity in the vertical direction at the top of its motion is always 0. It's got to stop at the top in order for it to come back down when we're speaking vertically. The initial velocity in the y direction is a sine beta, if we go ahead and look at our little vector diagram on the left side there. And we can go ahead and use that, also knowing the acceleration of gravity, to come up with an expression for the time. So we see that the time is equal to v naught y, initial vertical velocity, divided by gravity. And then to find the maximum displacement, we know that that's our delta y, or delta x if you want to think of it as. So we have to use that equation to ultimately solve for that. Now we're going to plug in v naught y over g in for our time values into that equation. So at this point it's literally just a matter of substitution and multiplying things out and figuring out what it turns out to be. So if you follow the steps, you can see that the final answer is a squared sine squared beta over 2g. For number 28, the answer is A, and the reason for that is the tangential acceleration is how fast is it speeding up or slowing down perpendicularly to the string. So because at the bottom of its motion, it's not speeding up or slowing down technically, that means that the tangential acceleration is 0. If you think about a pendulum as it swings, on its way down it's speeding up, and on its way up, as it passes the halfway point, the middle there, then it starts to slow down. So right there in the middle, right at equilibrium when it's vertical, that means it does not have a tangential acceleration. Now the reason why we say tangential is 0 and not just acceleration is technically it's moving in almost a circular pattern, so really you could say that there's a centripetal acceleration. But again, that's not what the question here is asking. Number 29 is a resistance problem where the resistivity, rho, times the length of your wire divided by the area gives you your resistance. Now it's the same material for wire X and Y, so the rho is the same. The length looks like it's halved, and now it talks about the diameter being twice as much. So now we have to really think about this as, well, we know that the diameter, in terms of the radius, the diameter is twice the radius. And if we think of a wire, if you cut a wire, that cross-sectional area is really a circle. So that area value there is really pi r squared. And in terms of diameter, again, diameter divided by 2 is the radius. So we substitute that in. In any case, whether we think about it as radius or diameters, we're ultimately squaring that d value. So because the diameter is twice as much, we know that that 2 squared in the denominator is going to bring it up by actually a factor of 4. So 1 times a half, because the length's a half, divided by 4 squared gives us an eighth of the initial resistance. Number 30 is an interference problem. So when two waves travel at each other, they can either be constructive or destructive interference. Constructive if they're on the same side of the medium, so they construct to make a larger amplitude. So if we have one that's 4 centimeters and one that's 6, the maximum height that it can be is 10 centimeters. Now if they're on opposite sides of the medium, destructive interference, that would mean that could get down to as low as 2 centimeters, the difference. So that gives us a range of 2 centimeters to 10 centimeters. Number 31 is really a torque problem. We're talking about torques, and we know that torque is radius times force. So the only way we can get, since we have F1 and F2, which are parallel to the surface of the table, so the little picture there is really an aerial view of this bar that's on this table. The only way we can get the torques to cancel out is if the forces are acted upon at the same point. Otherwise, if they're not at the same point, then the torques are going to be different, which will then mean it can accelerate.